Let's start the course by understanding the problems of a typical DevOps process. And throughout the course, we will discuss and learn how GitOps can be used to overcome some of these problems. Dasher is a software vendor that provides a platform to help businesses connect data, applications, and devices across on-premise environments. Of late, their R&D team is exploring the option to move their services to the cloud and benefit from container technologies. They have come up with a Task Dash DevOps team who will be setting up the project from scratch following some of the industry's best practices. They will be working on a multi-cloud infrastructure using Docker for containerization and Kubernetes for container orchestration. The team starts with the infrastructure as code concept to manage and provision their infrastructure through code instead of manual processes. They also followed other concepts like policy as code, configuration as code, and network as code. Following the X as code approach, the team avoids the manual process of setting up infrastructure, networking, and deploying applications to, let's say, a Kubernetes cluster. Instead, the team can use Terraform or Ansible scripts to set up the infrastructure using YAML and other configuration files. Each user had these configuration files on their machines and were manually executing them to create the cluster and the applications. For central access and version control, all code and configurations were stored on a single master branch in a Git repository. Any new changes were directly pushed to the master branch, and hence there were no code reviews or automated tests to check the configurations. As there is no automation, for any changes to the infrastructure, the users had to manually connect and execute commands that raises another challenges to tracing changes and who executed what. To overcome this, the team has set up a CI/CD process. The CI pipeline automates the build, test, and containerization process for applications, and for deployment, the CD pipeline follows the traditional push-based approach using kubectl commands to push changes to the Kubernetes cluster. Parallel to the CI/CD process, the team is also making changes to the infrastructure and application resources within Kubernetes manually through the command line interface. This approach has a few problems, like using the CI push-based model or making manual changes through a CLI possesses security issues as it requires exposing credentials outside of your cluster. There are ways to secure credentials in CI/CD and CLI, but it is generally not recommended as it is a very well-known attack vector for the CI/CD systems. Since the users are making manual changes to the cluster through CLI and other means, it leads to configurational drifts. Let's also not forget about the cloud computing disasters. It could happen anytime and could be anything like natural disasters such as earthquakes or floods, or technical failures such as power failure or network connectivity. And it could also be human actions such as misconfigurations or unauthorized modifications. During disasters, the team should have disaster recovery plan to recover the infrastructure and the application state. The configurations can be referenced from the desired state in Git, but the problem is the configuration in Git is not the latest one, as manual changes were done directly on the cluster or infrastructure by the team using CLI and other means which were not part of Git. So once the infrastructure and Kubernetes are back running, the team has to go through a painstaking process to figure out what changes were done manually and repeat them to get the desired state. These problems could be overcome using the GitOps methodology. What is GitOps? GitOps is a framework where the entire code delivery process is controlled via Git. which also includes infrastructure and application definition as code and automation to deploy changes and rollbacks. GitOps can be considered as an extension of infrastructure as code that uses Git as the version control system. Developers commit to a shared repository using a version control system such as Git. Usually, a feature branch is created, which is a copy of the main codebase, where a team of developers can work on a new feature until it is completed. A continuous integration service automatically builds and runs unit tests on the new code and merges the code into a central repository. Before merging, the changes are reviewed and approved by the concerned team. A continuous deployment is the final stage in the pipeline that refers to the automatic releasing of any developer changes from the repository to the clusters. The core idea here is to have the infrastructure, applications, and all related components declaratively defined in one or more Git repositories. In the GitOps scenario, an automated process ensures that the desired state in the repository and the actual state in the production environment always matches. A GitOps operator runs within one of the Kubernetes cluster. It continuously monitors and pulls changes from Git repository and applies them within the cluster it is running. And it can also apply them in a different cluster as well. Meanwhile, if a developer merges new code to the application Git repo, an automated CI process kicks in and does a round of unit testing, builds the application, creates a Docker image, and pushes it to the container repository. And finally, it also updates the Kubernetes manifest within another Git repository. The Git operator identifies the difference between the desired state in the Git repo versus the actual state in the cluster. It pulls the changes and makes sure that the desired state always matches the actual state. GitOps also eases the rollback process. Since all the code is version controlled in Git, a team member can issue a simple git revert command to go undo any changes which are made earlier. Since the repo is continuously monitored by a GitOps operator, it picks up the changes and rolls back to the previous state. Thank you. Let's talk about GitOps principles. GitOps has 4 principles. The first principle is about the declarative versus imperative approach. GitOps demands the entire system, including infrastructure and application manifest, to be declared in a declarative state. It discourages the use of the imperative approach as it uses a series of explicit commands to change the desired state. The imperative approach also makes reconciliation difficult because it does not store any state. The second principle is to make use of Git. All the declarative files, also known as the desired state, is stored in a Git repository. Git provides version control and also enforces immutability. Since the desired state is stored and versioned, it is essentially known as the source of truth state. Once we store the desired state in Git, we must allow any changes to the state to be applied automatically. This brings us to the third principle. GitOps operators, also known as software agents, automatically pull the desired state from Git and apply them in one or more environments or clusters. The GitOps operator can run in one of the cluster and can make or push changes to other clusters as well. The final principle talks about reconciliation. The GitOps operator also makes sure that the entire system is self-healing to reduce the risk of human errors. The operator continuously loops through 3 steps: observe, diff, and act. In the observe step, it checks the Git repository for any changes in the desired state. In the diff step, it compares the resources received from the previous step to the actual state of the cluster. And in the act step, it uses a reconciliation function and tries to match the actual state to the desired state. Thank you. Let's understand the difference between DevOps and GitOps. GitOps and DevOps do share some of the same goals with a few differences. GitOps is typically used with containerization technologies like OpenShift and Kubernetes, while DevOps can be used with any application. In a typical DevOps pipeline, a developer writes code using an IDE and commits them to a source code management system. A CI process picks up the latest code and runs through a series of stages to test and build the artifacts before creating an image and publishing it to a container repository. Then the continuous deployment pipeline connects with the Kubernetes cluster and applies a kubectl imperative command to push the changes to the clusters. Within the GitOps pipeline, we essentially have two Git repositories, one for the application code and the other for Kubernetes manifest. The continuous integration steps remains the same till publishing an image to the container registry, and the next step is to clone the manifest configuration repository and, for example, update the manifest with the new image name, commit, and push to the branch. And finally, the pipeline will also raise a pull request to the manifest Git repository. A team member will review the pull request, suggest any changes, or if everything is fine, approves it and merges the changes. At this point, the Git operator running within a Kubernetes cluster will pull the changes from the repository and synchronizes them within the cluster. To summarize, in the DevOps pipeline, the changes were pushed to the cluster, and in GitOps, the changes were pulled by the operator. In the next video, we will understand the pros and cons of both these approaches. Thank you. What is push or pull-based deployment? Most of the deployment tools use a push-based approach via a CI/CD pipeline. In a push-based approach, the application code goes through various stages of a CI pipeline, and the updates are pushed to the Kubernetes cluster. For pushing the updates, the CI system needs to have read-write access to the Kubernetes cluster. For this, we need to expose Kubernetes credentials outside the cluster and store them in a CI system. This raises potential issues and is not recommended. Apart from this, the CI system also has read-only access to the Git repository and read-write access to the container registry, whereas the Kubernetes cluster has read-only access to the container registry. Talking about the benefits of push-based approach, the deployment is not restricted to a particular plugin. In Jenkins CI, we have multiple plugins or approaches which can be used for a Kubernetes deployment. Secret management is made simpler by the fact that secrets can be used in pipeline. And the Helm plugins make it simpler and facilitate Helm chart deployment. And talking about the challenges of a push-based approach, the deployment approach is tied to the CI system. Today we use Jenkins and its plugins. Tomorrow we might migrate to Azure DevOps, and a lot of deployment approach should be rebuilt. And cluster login information is embedded in the CI system for deployment purpose, and hence the CI system has read-write access to the Kubernetes cluster. Talking about the pull-based approach, the GitOps operator deploys new images from running inside of the Kubernetes cluster. The operator can either check a container repository for new images or can check a Git repository for manifest updates. In a pull-based approach, the CI/CD system has read-write access to the container registry, and as we can see here, it does not have access to the Kubernetes cluster. Some benefits of a pull-based approach are: the deployment approach is not coupled to the CI/CD pipeline because the deployments are done on cluster internally. No external user or clients has the right to modify the cluster. GitOps operator supports multi-tenant model and can work with multiple repositories and namespaces. For example, Team Blue working on a Blue Git repository can use namespace Blue for deployments. Secrets can be encrypted using various tools and pushed to Git repository, or we can make use of HashiCorp Vault and replace placeholders values during deployment. GitOps operators can scan container registries for newer image versions and deploy the latest image in the Kubernetes cluster. And even the pull-based approach have few challenges. So the major challenge is about managing secrets in a pull-based model because it's a bit tricky compared to the push-based model. As per GitOps principles, even secrets should be declaratively published to Git repository. While deploying a Helm chart, managing secrets is harder because the secrets must first be encrypted using a tool like HashiCorp Vault or Bitnami sealed secrets, and then decrypted before passing on to the GitOps operator. Not only Helm charts, this approach remains the same for generic secrets deployments as well. So that is the differences between the push and the pull-based deployment models. Thank you. Let's have a look at GitOps features and use cases. As mentioned in one of our earlier sessions, everything must be declaratively stored in a Git repository. The Git repository contains the desired state and is known as a single source of truth. Since everything is stored at Git, the application rollbacks can be achieved using a simple git revert command, which reverts to the previous Git state. Because everything is done through a pull request, it also addresses the issues of audit trails. You only need to look into one area, namely the commit history, to find out why something doesn't function. CI/CD automation is a place where building, testing, and deployment will happen automatically, relying on the desired state within the Git repository. Continuous deployment of application is probably the most popular use case of GitOps. It automatically deploys the application to the clusters. Once we have adopted GitOps for our application, it is logical to apply the same for cluster resources and infrastructure as well. In case of Kubernetes, resources might be secrets, networking agents, service mesh, databases, Prometheus monitoring, and anything else. The automatic reconciliation of what is described in Git is one of the core principles of GitOps. It is always going to compare the desired state in Git with the actual state in the cluster. And at any given point of time, if someone unintentionally modifies the system, it will be reverted back to keep in synchronized with Git. One of the key distinctions between GitOps and other deployment techniques is its ability to detect configurational drifts earlier. The last feature is about multi-cluster deployment. Deploying to a single cluster is already a challenge on its own. If you have multiple clusters at different geographical locations, you need to track them down and understand how they are different. This is one of the places where GitOps excels because the state of all clusters is stored in Git. Moreover, a single GitOps operator can deploy applications to multiple clusters without the need for it to be installed or set up on all the clusters. Let's have a look at GitOps benefits and challenges. First, let's look at the benefits. GitOps is lightweight and vendor neutral. It's because the underlying Git protocol is open source and usable on a wide variety of platforms and setups. GitOps is also faster, safer, provides immutability, and reproducible deployments. So while working as a team, we often come across environmental changes, but being unable to identify what it is. It is most likely caused by a manual update by one of the team members. The GitOps operator can make sure that no changes are done to your deployment manually. It can also eliminate configurational drift. So let's assume, even after taking precautions, someone from the team manually changed or updated a configuration directly on the cluster. So here, the GitOps operator will fix that for you based on the desired state which is stored in the Git. And talking about the processes and the tools, most developers are familiar with using Git and CI tools for automation. And when using GitOps, the developer follows the same approach. The developer pushes the code as usual to the Git repository, which triggers a CI pipeline for test and deployment. Talking about revisions and history, we take advantage of the history tracking capabilities of Git. In order to identify differences between two declarative files, we may compare them and they can typically be linked to a specific change request. Now let's look at some of the challenges. So GitOps does not help with centralized, secret management. As discussed earlier, as per GitOps principles, even secrets should be stored in Git repositories declaratively. GitOps doesn't offer any way to help manage secrets. The ops teams needs additional tools to secure and use secrets with Git operators. And talking about the number of Git repositories, it is a huge disadvantage. Organizing Git repositories to handle multiple microservices across various environments is challenging because the number of Git repositories increases with every new application or environment. We need to decide whether to have source code and manifest in the same or separate repositories. And for multiple environments, we need to decide to use either separate repositories or multiple Git branches. When it comes to organizing your Git repositories, there is not one size that fits all. We should go with what is good to work best for our applications. We also have challenges with updates. So in a continuous delivery process, the application gets updated frequently and the CI process has to create the pull request. So conflicts can arise when multiple CI processes try to write to the same GitOps repository. So we need to have a manual solution to avoid this issue. And then we also have, governance, right? So here, GitOps relies on a PR, which is a pull-based approval model, where a PR approval is responsible for the review. So there is no way to enforce company policy rules once the PR is approved. And then we may also have issues with malformed YAMLs or configuration manifest. So users must rely on other tools to validate the manifest files. Let's have a look at all the available GitOps projects and tools at the time of this recording. In the context of this course, we will apply GitOps practices to Kubernetes applications. And for GitOps controller, we will make use of the argo1 project. argo1 is a declarative continuous deployment tool for Kubernetes. Apart from this, we have a lot of other tools which provides GitOps capability. So some of them are Atlantis, which is an application for automating Terraform via pull request. Then we have Auto Apply, which is a tool for automatically applying changes from a Git repository to a Kubernetes cluster. We have CloudBees Rollout, which is an advanced feature flagging solution that lets your development teams quickly build and deploy applications without compromising on safety. We have FluxCD, which is a set of continuous and progressive delivery solutions for Kubernetes. We have Helm Operator, which automates Helm chart releases in a GitOps manner. We have Flagger, which is a progressive delivery Kubernetes operator, which can do canary, A/B testing, and blue-green deployment automation. We have Ignite, which is a virtual machine manager with a container UX and a built-in GitOps. We have Pharos, which is a CRD-based GitOps controller. We have GitKube, which is a build and deploy Docker images to Kubernetes using Git push. We have Jenkins X, which is a CI/CD platform for Kubernetes that provides pipeline automation with built-in GitOps and preview environments. We have KubeStack, which is a GitOps framework using Terraform for cloud Kubernetes distributions like AKS, GKE, and EKS with CI/CD examples for common tools. We have Weave Cloud, which is an automation and management platform for development and DevOps teams. And finally, we have pipecd, which is a continuous delivery tool for declarative Kubernetes, serverless, and infrastructure applications. Thank you. So let's understand what is Argo CD, why use Argo CD, and how Argo CD works. Argo CD extends the benefits of declarative specifications and Git-based configuration management. It is the first step in achieving continuous operations based on monitoring, analytics, and automated remediation. It can deploy to multiple clusters and is enterprise friendly in terms of auditability, compliance, security, ABAC, SSO, and lot more. But what is Argo CD? Argo CD is a declarative GitOps continuous delivery for Kubernetes resources which are defined in a Git repository. It continuously monitors running applications and compares their live state to the desired state. It reports the deviations and provides visualization to help developers manually or automatically sync the live state with the desired state. So how does an Argo CD work? So it follows the GitOps patterns by using Git repositories as the source of truth for the desired state of application and the target deployment environments. Argo CD supports a lot of Kubernetes manifest in several ways, like customized applications, Helm charts, JSON files, YAML, or JSON manifests. It automates the synchronization of the desired application state with each of the specified target environments. Thank you. Before we talk about Argo CD architecture, let's have a look at Argo CD concepts and terminology. To understand and use Argo CD, one should be familiar with the basics of Git, Docker, Kubernetes, CI/CD, and GitOps concepts. In this slide, we will cover basic terminology specific to Argo CD. In Argo CD, we will be working and creating applications known as Argo CD application. An application is a custom resource definition which gets created when we install Argo CD. An application in Argo CD defines the source and destination for your Kubernetes resources. Similarly, we have an application source type which defines the tools which are used to build the application. It could be Helm, Customize, or others. And an Argo CD project provides a logical grouping of applications which is useful when Argo CD is used by multiple teams. The desired state of an application manifest stored in a Git repository is known as target state. The current or the live status of the application resources like pods, secrets, config maps deployed in the Kubernetes cluster is known as live state. When an Argo CD application is created, it tries to synchronize the desired state in Git to the live state in cluster. This is called as sync, and it reconciles the current cluster state with the target state in Git. An example of this could be, by applying changes to a Kubernetes cluster. A sync status lets us know whether or not the live state matches the target state. Is the deployed application the same as Git says it should be? And finally, a synchronize operation status let us know whether or not a sync succeeded. A refresh option compares the latest code in Git with the live state, figures out what is different, and can initiate an automated sync or ask the admin to sync manually. Argo CD also provides built-in health assessments or assessments for several standard Kubernetes resources. It provides an overall health application status as a whole. Let's have a look at Argo CD features. Argo CD has an option to automatically deploy applications to a specific target within multiple clusters. It also provides audit trails for application events and API calls. It can also integrate with various third-party products like GitHub, GitLab, Microsoft, LinkedIn for SSO integrations. It also synchronizes the application based on webhooks, and it can react to any push event to GitHub, Bitbucket, GitLab, and few other source code management systems. It also has an option to roll back to any application configuration which is committed in a Git repository. It also gives you a web UI which provides a real-time view of application activity. It can also automatically detect any configuration drift, and it can also give you visualizations to pinpoint the differences. It also provides out-of-the-box Prometheus metrics, so we can set up Prometheus and we can visualize the data using Grafana. It also supports multiple configuration management and templating tools like Customize, Helm, or even plain YAML configuration. It also has a lot of options like pre-sync, sync, and post-sync hooks to support complex application rollouts like blue-green deployments and canary upgrades. It also supports multi-tenancy, and you can also create custom airbag policies for different authorization roles. It also provides a CLI and supports access token for automation through CI integrations. It also provides health status analysis of all the application resources, and we can also create our own custom health checks as well. And it also provides an option to automatically or manually synchronize an application to its. Let's have a look at Argo CD architecture. Let's assume we have a Kubernetes environment and Argo CD is installed as a Kubernetes controller within the Kubernetes environment. Users can access and make changes within Argo CD either using a CLI or through a user interface. Some of the operations could be like creating Argo CD applications, managing existing projects, setting up single sign-on with external providers, and synchronizing options. Argo CD continuously monitors running applications and compares the current state against the desired state in the Git repository. Any changes made to the desired state in the Git repo can be automatically pulled and applied in the specified target environments. We can also configure a webhook on Git repository, which is going to notify Argo CD based on Git events. The Argo CD API server is a gRPC REST server which exposes the API. This API is consumed by the web UI, CLI, and can also be used within CI/CD systems. In this illustration, we have Argo CD controller implemented within the Kubernetes dev environment. The same implementation can also connect and deploy resources to other Kubernetes environments as well. This is known as multi-cluster deployment. Argo CD also exposes different set of Prometheus metrics which can be visualized through Grafana. And it also has an out-of-the-box notification service with various triggers, message templates, and can notify multiple third-party services like Slack, email, and GitHub. Thank you. Let's have a look at Argo CD installation options. Argo CD has two types of installations, multi-tenant and core. A core installation is best suited for users who use the Argo CD alone and do not require multi-tenancy. This installation is simpler to set up and has fewer components. The bundle installs the minimal non-HA version of each component and excludes the API server and user interface. The multi-tenant is the most popular method for installing the Argo CD in the multi-tenant installation model. This kind of installation is often utilized by organizations' various application developer teams and is kept up to the date by a separate platform team. In this method, there are two different installation options available, high availability and non-high availability. The non-high availability option is not suggested for use in production. It can be used during the evaluation phase, for testing, and for proof of concepts. And again, it provides two manifests, install.yaml and namespace-install.yaml. The install.yaml manifest provides a standard installation with cluster admin access to Argo CD. If you intend to use Argo CD to deploy applications in the same cluster where Argo CD is running, use this manifest set. With provided credentials, it will still be able to deploy applications to remote clusters as well. And then we have the namespace-install.yaml manifest. This provides an installation which only requires namespace level access. So we need to use this manifest if we want Argo CD to rely on provided cluster credentials and don't need Argo CD to deploy applications in the same cluster that it is running in. And of course, with provided credentials, it will still be possible to deploy applications within the same cluster. And for production use, we use the high availability installation option, and the components in this are identical but have enhanced for high availability and resilience. It again provides two manifests, which are ha/install.yaml and ha/namespace-install.yaml. Both these manifests are same as compared to non-HA option, but with multiple replicas for supported components. In this course, we will be using the install.yaml manifest from the non-HA available version and install it within the Argo CD namespace. Argo CD can also be installed using Helm. So this is a community managed or maintained chat, and by default installs the non-HA version of Argo CD. After installing Argo CD, to interact with the Argo CD API server, we need to download the CLI from its GitHub repository and move it to our user local bin directory. In the upcoming hands-on lab, we will set this up, log in, and interact with the server using the CLI commands. Thank you. Okay, so let's start by installing Argo CD and Argo CD CLI. So for doing this, let me go to the Argo CD's official documentation. And here we can go to the Getting Started page. Within the Getting Started page, if you see, we can install Argo CD by creating a namespace called Argo CD and by just applying the manifest. So this is the stable manifest, okay? And then you can also see that we can download the Argo CD CLI and you can install it within your machine, right? So let me just go to the releases page in GitHub. And the current version at the time of this recording is 2.4.12. So let me go to releases. So I would like to use the 2.4.11 version. Okay, and here if you see, we have a couple of options, right? We have the non-HA version as well as the HA version, and if you want to also install the CLI, we can get that in the assets. So let me just use the non-HA version. Let me just copy both the kubectl commands, and I would like to run this within my Kubernetes cluster. And talking about my Kubernetes cluster, so I am using a single node Kubernetes cluster for the demo purpose, right? So it is using Kubernetes version 1.2.4.3. So if you currently see the namespaces, we don't have anything fancy over here. So these are the default Kubernetes namespaces. So let us go ahead and install argo CD over here. So this is going to set up all the required services. So let us quickly check the argo CD namespace, right? So let me just decrease the font a bit over here, right? So you could see a lot of deployments, pods, and services being created for us. And currently these are in creating state. So let's give it a few minutes. Okay. So let me just check them again. Okay, so if you see here, all the pods are currently in running state. And if you see the pods, we have the application controller, the text server, the notification controller, Redis, repo server, and the Argo CD server. Along with that, you also have various services also present as part of the manifests. And we are interested in the Argo CD server for the time being. Okay, so let me just get the services. So here, if you see the services, currently all the services are of type cluster IP. So we are interested in the Argo CD server, which is going to give you the user interface. And let's try to change this to node port. So let me just quickly edit the service Argo CD server, and let me just change the type to node port. Okay, it took 10 seconds for me to edit that. So the Argo CD server is now accessible on port 30663. So let's go ahead and try to access this port. So this is currently running on a public Kubernetes cluster. So I should be able to access this using the IP address of my server along with this port number, right? So the IP address is 139.59.21103. So let me just quickly open that. Let me just check this again. Okay, so currently this will be listening on a private certificate or a self-signed certificate. So the connection is not private. So you just need to accept the self-signed certificate. And this is the UI you will be getting. So the first thing what we can do is we can try to log in. So the username by default is admin, but what about the password? You should know what password you need to use for logging in. So in order to get the password, we can go back to the Kubernetes cluster, and within the Kubernetes cluster, I can search for the secrets within the Argo CD namespace. So you can see here, it comes up with the Argo CD initial admin secret, the notification secret, and some secret. Okay. So for me, we'll currently look into the Argo CD initial admin secret. So let me try to fetch this. I want to get this in JSON format. I want to use JQ. Okay, let me just get this in JSON format. And if you see here, we have a password field, and this is currently in base64 encoded format. So let's try to decode this and use it for logging in. So I can simply use JQ dot data dot password, right? So let me just pipe this to a base64-d. And this is the password which can be used for logging into argo cd. So let me just copy the password, go back to the browser, paste it, and click on sign in. So now you're signed in to the user interface. So currently you won't have anything. You don't have any applications because we have just installed Argo CD. You can also check. I mean, if you want, you can create repositories over here, which can connect with your GitHub repositories or Helm charts. You have various options for configuring certificates for the Git repositories, uh, connecting or configuring to multiple Kubernetes clusters, creating Argo CD projects, and also configuring accounts as well. So let me quickly update my password over here. So I can go to the user info. And if you see here, currently I'm logged in as admin, and this was issued by Argo CD because this is the default user. So let me quickly update my password because I obviously won't be able to remember the randomly generated password. Okay, so I just updated my password over here. And if you want to read the documentations, you can go to the last tab, right? So this is how the UI looks like. And since I have updated the password, it is going to automatically log out and ask me to re-log in using the updated password. Right, so this is how the UI looks like. So we will be exploring other options in the UI as we move forward, but for the time being, let's also install the CLI so that we can access the Argo CD server, the applications through the CLI as well. So I can go to releases. In the 2.4 level release, I can scroll down and we have various assets over here. So let me just take in the Linux AMD 64 asset. Let me copy the URL. So within the server or within my Kubernetes cluster, so I can simply go use a simple duplicate, paste in the URL. So it's around 125 MB. So let's give it a couple of seconds. So now, so we should be having the Argo CD Linux AMD 64 downloaded. So let me just rename this to Argo CD. Okay. So let me make this executable by executing the chmod +x command. And let me move this to the user local bin directory. Okay. So now Argo CD should be accessible. So if I do Argo CD from the CLI, if you see, it gives you all the options over here. So you can use Argo CD to manage the accounts. You can use it for administration purpose. Whatever basically you can check and do in the UI, the same things can also be done using the user interface or using the CLI basically. So let me quickly log in for the time being. So you have a login option over here. So I can do Argo CD login. And if you see here, by default, the login function, expects the server IP address. Okay. So let me, get the Argo CD server IP address. So I can do Argo CD login, and the server IP address is 10.98.110.228. So I can do 10.228. Okay. Since we are using a self-signed certificate, so I'm just going to accept this. And you need to use your credentials for logging in. So let me just use admin because that is the only user we have at this moment, and the password. Right, so we are successfully logged in. So now I can use Argo CD app list. So currently, if you see, this command returns nothing because we have not yet, created any Argo CD application. So this will be empty, but I can check out the Argo CD cluster list. Right? So by default, when we install Argo CD within a Kubernetes cluster using the non-high available manifest, it is going to also, make the cluster where we installed it as the target. So it should be able to, deploy applications to this cluster. So in the upcoming sessions, we'll also make sure that, this Argo CD installation, can deploy applications to multi-clusters as well. Okay, so far we have created or we have